How's everyone doing today? Today we're going to talk about some theoretical probability of simple events. We are going to be discussing and implementing our understanding of experimental probability and theoretical probability to theoretical probability today. Remember that experimental probability is the number of outcomes over the number of total trials. So we do an experiment, therefore experimental probability. We figure out how many total times we did it, how many times did what we want happen. That's our experimental probability. Theoretical probability is the number of ways the event can occur over the total number of equally likely outcomes. So there might be a excuse me, let me back up for a second. The number of ways that the event can occur is the number of ways that we are getting the answer that we are requesting, okay, that we are going to try to find out, that the question is asking. And then we have to ask ourselves, what is the total number of equally likely outcomes? And we're going to discuss that a little bit more today. So if we go through our online learning here, we are going to see that we come up across a really great example of theoretical outcome already. So it says the number of balloons in the game. If he pops a blue balloon with a dart, he wins a prize. If we go through the understanding and development of this balloon game, we see that there are 4 balloons on the left, 2 balloons on the right that are blue. Excuse me. On the left, you have 4 out of 12 balloons that are, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yes, there are 4 blue balloons out of 12 that are blue. So there are 4 chances to win a prize. On the right side, you have 2 blue balloons out of 8. So, do I have a better chance of getting a prize in the left game or the right game? Which game do I choose? Well, in game 1, I have 4 chances out of 12. So my total number of ways the event can occur, 4, over the total number of equally likely options. So I could hit a red, a yellow, I could hit a blue when I throw a dart, right? It's not an experiment. We're not really experimenting right now. We are just throwing a dart and we're going to hit a balloon. We could equally likely hit a red, yellow, or blue, all of which have the same amount of space, same size, color, density, all that kind of stuff. So there are 4 blue balloons and there are 12 balloons total. Okay, so I could equally likely hit a blue balloon or red or yellow 12 times in the left game. What is the percentage of hitting a blue one? 4 out of 12 because there are 4 blue balloons. What about the right game? Well, there are 2 blue balloons. Whew, there's a lot to say, I promise you. On the right side here. And we will see that there are 8 total. Same thing applies. I want 2 events to happen, so the number of ways the event can occur, hitting a blue balloon, over the number of ways that could happen. So there are equally likely ways to hit a red and a yellow balloon as well. So that would be 2 out of 8. Remember, reduce fractions. Reduce. If you can reduce a fraction, reduce it. Okay? Do not leave an improper fraction. Do not leave an unreduced fraction. Reduce the fractions, please. So you should get an answer of 1/3 and 1/4. And we can see that game 1 is going to be your better option to play because 1/3 is a more likely chance to happen than 1/4. So if we move on to our spinner section here, you're going to go through the selection boxes, and I feel like that's pretty self-explanatory. You can see the number of sections that each spinner has. The one on the left has 4. The number on the right has 10. The spinner, we're trying to figure out which spinner will give the best chance of winning. The winning space is A. So if we land on A, we win a prize. How many sections of A does spinner 1 have? It has 2. How many sections of spinner 4? There's 4. Or spinner 2, spinner 4. My goodness, all these numbers. Crazy. For each spinner, what is the ratio of selections labeled A to the number of selections? Remember, the ratio is our theoretical probability. So the number of times that the event can occur in spinner 1, if we're trying to get spun to the A section, is 2. How many times can you land on a section in spinner 1? 4. So spinner 1 is 2 out of 4. There are 4 A's on spinner 2. That means I can land on 4 sections of spinner 2 and get my correct event. I could also land on the other events, which make a total of 10. So there are 10 sections on that spinner. I want to land on the 4 of them. So my ratio would be 4 out of 10 for spinner 2 and 2 out of 4 for spinner 1. What was one way to make the ratios in part C easier to compare? Well, if we really want to compare both numbers. So if you look at 2 out of 4 and 4 out of 10, you could divide both of those and find the percentage to compare the percentage, which one is the better percent, right? Well, if you wanted to do it really quickly, you could also make both numbers into a common denominator. The common denominator would be 20. If we made both of them kind of common denominators, we would have spinner 1 be 10 out of 20 and spinner 2 be 8 out of 20. And once we have those numbers, we could see that the better ratio is 10 out of 20 because there's more likely chance to have a spinner 1 chance happen than spinner 2. Here's my suggestion. My suggestion is that you take the theoretical probability outcome. For example, 2 out of 4, 2 over 4. Divide 2 by 4, okay, and you are going to get 0.5. 0.5 into a percentage is 50%. We all know how to turn a decimal into a percentage. We've gone over that in class many times. 4 out of 10. 4 out of 10 gives you a 0.4 percentage, or 0.4 decimal. Turn that into a percentage, it's going to be 40%. Which one is more likely, the 2 out of 4 or the 4 out of 10? The 2 out of 4, because that was 50% versus 40%. So make these into percentages and you will be very successful, okay? So if the common denominator thing is beneficial for you, absolutely by all means use it. But my recommendation is turning those numbers into percents. So really we have an understanding and we kind of go over the vocabulary of what theoretical probability is. Remember that theoretical probability is the number of ways an event can occur over the total number of equally likely outcomes. In our next example here, we're drawing tiles from a bag that have a total of 20 tiles in that bag. The tiles are the same size and cannot be told apart by touch, so equally likely to get any tile, very important part. What is the theoretical probability she selects a red tile? Well, there's 5 green, 6 red, 9 blue. That is equal to 20 tiles. Perfect. So there's 20 equally likely chances of getting any tile. Or 20 equally likely outcomes in our sample space, the total number of ways or outcomes that there are going to be. There are 6 red outcomes. So I could go in there and there are 6 tiles that are red. So if I want to find my theoretical probability, the number of ways an event can occur, picking a red tile. 6 ways that can occur because there are 6 red tiles. We have to put that number over the total number of tiles or the total number of equally likely outcomes. There are also, in total in that bag, there are 20 tiles that are the same touch, same size, same feel. We could equally likely pick any number of any tile in that group of 20. So the ratio or the fraction is going to be 6 out of 20, or reduced is 3 out of 10. If I turn that fraction into a decimal, I get 0.3. and then into a percentage, I get 30%. So it is 30% likely that I'm going to be grabbing a red tile out of that bag. The next problem is a coin problem. I'm going to let you do that by yourself. It's the same type of theory and same type of math involved. So now we're going to move on to understanding the theoretical probability of compound events or more than one event happening. Remember, compound, a combination. I talked a lot about that in experimental probability, is combining more than one event. So compound events, combination of more than one event. That's how I remember it. You're welcome to use that or whatever you need for your own idea. If we go through the understanding here, we can go through this chart and we are seeing that we have two spinners, labeled 1 through 4. Each spinner, of course, is equally likely, has the same colors, same numbers, same sizes. We want to find the probability that the sum of the two spinners lands on 3. So if we fill in our chart, and they give us a chart with our answers down below here as well, we can see that there are 2 ways to get 3, 1 way to get 2, 3 ways to get 4, 4 ways to get 5, 3 ways to get 6, 2 ways to get 7, and 1 way to get 8. So when they're asking us what is the theoretical probability here, there are 2 ways to get 3, okay? There are also 16 equally likely outcomes in this space. Well, remember, the number of outcomes that the event could occur, that we want the event to occur, is 3. The number of total outcomes is 16. So we do 2 over 16. And that gives us an fraction of 1/8. So, again, let's back up for a second. The number of outcomes we want, which is 3, happens twice. There are 16 spaces or 16 outcomes that could happen. My probability of getting a 3 would be 2 over 16 because it's the total number of outcomes that add to 3 over the total number of outcomes in the sample space that's provided. 2 over 16 again is 1/8. If we move down to here, which is more likely? The probability of getting a 3, or which is equal to the probability of getting 3? Well, if we notice, there are also 2 ways to get 7. Well, if there's 2 ways to get 3 and 2 ways to get 7 in the same sample space, those fractions and those percentages are going to come out the exact same. So the probability of getting a 3 is exactly equal the probability of getting a 7. If we move on to our tree diagram, I know that in the 6th grade you have done tree diagrams before, understanding probability. Now we're really kind of going into what this means, and we're moving away from being able to draw a tree diagram into really understanding what that tree diagram means and using numbers to represent that versus handwriting all of that information out. So they did provide a nice tree diagram for us for picking out a wardrobe here. You could have black or white shorts, red, blue, or green shirt, tan or brown shoes, and you have the number of selections. For our first question here is, choose the number that makes the sentence true. The tree diagram shows there are how many equally likely outcomes in the sample space? Well, a nice trick for me when I read tree diagrams is I go all the way to the right side. And if I go all the way to the right side, I can count the number of times that there are boxes there. If I count all those boxes, I get the number of 12. Why? Because if I follow the tree diagram, I can go black, red, brown, black, red, tan, black, blue, brown, black, blue, tan, black, green, brown, black, green, tan, white, red, brown, white, red, tan, white, blue, brown, white, blue, tan, white, green, brown, white, green, tan. And the number of times I said that is 12. How did I know that right away? Well, all I did was I tracked across the tree diagram and I found my last response to be where the shoes are. And my tree diagram, the way that I drew it out, the way that they drew it out, the way that I'm sure that you would have drawn it out, has 12 selections there. So there are 12 equally likely outcomes in the sample space. So which shows the probability of a white, blue, tan? Well, There is only one way to get white, blue, and tan out of this tree diagram. Well, the number of remember theoretical probability, number of ways the event can occur over the total number of outcomes. There are 12 outcomes that could occur. We want one of them, so the fraction is 1 over 12. The ratio is 1 over 12. If we go a little bit more, what is the ratio of white shorts with blue shirt? Doesn't matter what shoe. Well, if I go from white to blue, ooh, there's a brown shoe or a tan shoe. That gives me 2 selections. How many is there total? 12. What is the number of outcomes that I want? 2. So 2 over 12, or reduce that fraction, gives me 1 over 6. My recommendation is for you to finish this section out by yourself. It's the same exact thing that we just talked about. Instead of a tree diagram, it really shows you kind of a 27 equally likely outcome sample spaces when you draw these cards here. But I will let you do that on your own. Please make sure to ask Mr. Kaufman any questions about either experimental probability or theoretical probability. Those quizzes there is a review quiz already posted on Google Classroom, and there will be a real quiz tomorrow to finish up the semester. Now, with that being said, please, 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 please turn in any work. If you do not turn in the work, you will not be in good academic standing. So all zeros in the gradebook need to be turned in by June 3rd. Okay, or June 2nd, excuse me. Basically, get them done as soon as you can. Thank you. Have a wonderful rest of your weekend, wonderful rest of your week. Good luck on that quiz tomorrow. Make sure to Google chat and video chat me if you have any questions. Take care.